Welcome to Cloud Native Data Virtualization on AWS. My name is Tom McMeekin, Solutions Architect, and in this session we'll explore how new Amazon Athena features like federated query and user-defined functions pave the way for lightweight Cloud Native data virtualization that can enable users to explore and query a variety of data sources through a single interface. This is a 300-level session and assumes some knowledge of the AWS Analytics Services. First, I want to start with taking a look back at how the evolution of application architectures have evolved and influenced data architectures over time. We've seen the evolution of application architectures go from mainframes to client-server to three-tier and to today, where microservice application architectures are enabling developers to build cloud-native applications faster and to scale easier. In parallel, so too has the data architecture evolved, evolving from predominantly being relational and monolith to now where application builders no longer need to make trade-offs between functionality, performance or scale, and can choose the right database to meet the specific needs of the application. And AWS has responded to these customer needs by providing purpose-built database services to meet their specific application requirements. With these services, developers can choose the right database service to fit their individual use case. While the value of choosing purpose-built databases is high for application development, the distributed nature of today's data architectures has a tendency to create isolated islands of data. Now, deriving insights from these data silos would typically involve manual effort to explore and access the data and a traditional integration approach of physically moving the data, transforming it, and preparing it for consumption. The integration also requires coordination with various teams to operationalize and maintain. And in order to ensure that the data consumed is not stale and remains current, managing the data lifecycle is super important to ensure the data remains consistent. But also, as data is replicated across the landscape, data governance becomes increasingly critical to get right. And now, embedding machine learning into your application creates a massive opportunity for you to deliver value from your data. But the typical skill sets required to do this is sometimes beyond an analyst function and requires the understanding complex programming and data science methods. And ultimately, as these dimensions compound, organizations are faced with the risk of a long time to value to use data effectively. Now, one approach to addressing these data integration challenges with connecting data sources to consumers in a complex data landscape is a data architecture practice known as data virtualization. Data virtualization presents end users with a uniform abstracted data layer so that the data sources can be accessed uniformly with a minimal movement. From an end user perspective, this is similar to accessing a single local data source with the ability to create a virtual data model by combining data objects from various data sources. So let's take a look at some of the core capabilities required to enable this. First, there needs to be both north and southbound interfaces to provide end user and data source interaction. Next, we need metadata management, responsible for cataloging, lineage, and data discovery. Now, alongside this, we need a query engine which provides query planning, optimization, and a platform for executing your queries at scale. We also need some form of resource management, providing resiliency and of the platform and load management and scalability. And finally, but most importantly, is security, where we need to be able to define policies and controls to provide granular access and auditability. Now, AWS provides services and features which enable these key capabilities. AWS features like newly introduced federated query and user-defined functions available in services like Amazon Redshift and Amazon Athena, coupled with AWS services like AWS Lake Formation, AWS Glue, AWS Lambda, and other core operational and security services, pave the way for orchestrating a lightweight cloud-native data virtualization on AWS. Today, we're diving deep into the new Amazon Athena feature, federated query and user-defined functions. So what is a federated query? Well, Amazon Athena was launched in 2016 and has provided customers serverless interactive query capabilities for the data stored on Amazon S3. Federated query is a new feature that enables data analysts, engineers, and data scientists to execute SQL queries across data stored in relational, non-relational, and custom data sources. With Athena Federated Query, you can submit a single SQL query and analyze data from multiple sources running on premises or hosted in the cloud. So Amazon Athena Federated Query is super easy to use. To get started, there's 3 simple steps. First, we need to deploy a data source connector. Now, this is our interface between our query engine and our data source. Next, we register our data source connector and associate a data catalog name. And finally, we write and execute our queries. So let's double click on the data source connector element and take a look at the anatomy of a federated query. So think of a connector as an extension to Athena's query engine, where code hosted in AWS Lambda is used to translate a query between your target data source and a SQL query in Athena. The beauty of using AWS Lambda as an integration layer is that it inherits all the scaling, availability, and pay-per-value benefits serverless provides. Connectors use Apache Arrow as the format for returning data requested in a query, which enables connectors to be implemented in languages such as C, C++, Java, Python, and Rust. Athena will fan out the Lambda functions in parallel, reading metadata and data of the specified data source. The number of these fan-out invocations depend on the Lambda concurrency limits within your account. Connectors also have built-in congestion control to handle federation to data sources that may not be as scalable as Athena and Lambda. You can also combine multiple catalog and data sources into a single query. So let's dive into this in a little bit more detail and see it in action. Today we're going to look under the covers on how you can use Athena Federated Query to bring together a heterogeneous data sources, apply machine learning and data redaction to build out visualization using Amazon QuickSight. So here's an example of a dashboard hosted on Amazon QuickSight that provides insights into the current sales and order status for an organization. Today in the demo, we'll be building a dashboard similar to this. You will see how insights on the dashboard can be derived from various different data sources and database technologies without the need to perform heavy data movement using traditional data integration methods. Here we have a combination of relational, in-memory, document, and key value data sources being queried using federated queries. Additionally, you will see how to embed machine learning via SQL to enrich your ordered data to perform detection of anomalous orders made by customers. And we'll establish lightweight controls to perform data redaction on sensitive data to prevent exposure. Now, the data architecture used to drive today's demo dashboard is a fairly typical environment where we have datasets distributed across purpose-built databases. The data landscape today is all hosted in the cloud, but you could easily extend this pattern to include datasets hosted on premises as well. Our dataset is based on the TPC benchmark dataset, which consists of tables residing on Redis on Amazon Elasticache, Amazon Aurora MySQL, HBase on Amazon EMR. Now today we're going to show you 3 demos. The first demo, you'll see how easy it is to federate to our parts and part supplier data sets stored on Amazon DynamoDB to Amazon Athena. Amazon Federated Query provides our query engine that is able to query the distributed data sets through a single interface. Now in a second demo, you will see how UDFs hosted on AWS Lambda can provide data redaction of customer-sensitive information. And then finally, you will see how easy it is to perform machine learning inference from Athena using SQL for detection of anomalous orders made by our customers. Let's now jump into the console to understand how easy it is to integrate our new data source into Amazon Athena. So before we build the dashboard, let's take a look at Federated Query from the Athena Query Editor. The first thing I want to draw your attention to is that the new features like Federated Query are only available when you upgrade to Athena Engine version 2. Athena Engine version 2 was launched at reInvent 2020 and unlocks Federated Query and other new features for you to access. So this is a critical step for you to do before following along within your AWS account. So in the demo environment, we have 3 out of our 4 data source connectors configured. We have our HBase connector querying our HBase environment on Amazon EMR. We have a JDBC MySQL connector querying our Amazon Athena Aurora MySQL environment. And we have a Redis connector querying our Redis on Amazon Elasticache environment. Let's quickly run some simple select statements to individually query our data sources. Now, as we click Run, Athena behind the scenes is evoking the AWS Lambda functions for each of the corresponding data sources. So we've just quickly run a simple select statement across our relational and non-relational data sources. Now on the left-hand side, if we select the drop-down box alongside, we'll see our Glue data catalog and the corresponding catalogs for each of the federated data sources. So if we click on the MySQL catalog, we can see the various databases we have hosted on our MySQL environment. If we select the sales database, we can see the defined tables and the corresponding metadata. So you can see how easy it is in the browser to quickly browse and query the federated data sources through our one interface. So let's now go ahead and deploy and configure a connector to our DynamoDB tables, which are hosting our parts and part supplier information. So to do that, let's click on the Connect Data Source. And this will take us to the configuration screen where alongside S3, we can choose to query a data source, which indicates we want to use federated query to query a data source, and then we're going to choose our data source. And you can see a bunch of different data sources available for you to use. So let's select Amazon DynamoDB, which takes us to the connection details page, where we need to specify the Lambda function which will provide the query translation between Athena and DynamoDB. Now, at the moment, I don't have a DynamoDB Lambda connector configured. So let's now go ahead and configure this. If we select to configure a new Lambda function, this will take us to a provided Amazon DynamoDB connector Lambda function template, which we can use to deploy our DynamoDB connector in your account. So let's go through some of the parameters we need to define in the right-hand side of the screen here before we can deploy the connector. We'll leave the application name as the prescribed default. We also need to configure our spill bucket. Now, the spill bucket is an S3 bucket where the data is returned to if, during a query, the Lambda invocation exceeds the Lambda limits, like a timeout or memory. So I'm going to copy in a bucket name that I've previously deployed. The next thing is we need to specify a catalog name. Now, this is the name associated to the Athena catalog. So within our queries, we'll be referencing Dynamo, where we want to query a DynamoDB table. We also want to retain encryption for our spill data, so we will keep this configuration to false. We will also keep our Lambda memory and Lambda timeouts configurations as the default. And then finally, we will create a unique spill prefix to store our spill data against in our spill bucket. We'll acknowledge and accept that this template is going to create custom IAM roles. And now we can select deploy, which was going to initiate a CloudFormation deployment to deploy and configure our Lambda data source connector for DynamoDB. Now, this will take a couple of seconds for us to deploy it. Okay, now the deployment is complete. You can see the Lambda function and the IAM role deployed as part of the template. So let's now go back to the Athena console to complete the configuration. After a quick refresh, we should now see the DynamoDB Lambda function listed alongside the other pre-existing connectors. So if we select that, you can see the Lambda ARN for the function we just deployed. Now, the last step we need to specify is our catalog name. So using the same name of the catalog as we specified earlier, Dynamo, and then we can hit connect. And now we have our DynamoDB data source connector deployed and configured and registered and alongside our Glue catalog and the other 3 data source connectors already deployed. So let's now head back over to run some queries against this data source connector. But before we do that, let's browse the metadata of our DynamoDB tables using the new connector. So if we select the data source drop-down list again and choose Dynamo, we should now start to see some of the metadata of our DynamoDB tables. Here we can both see our parts and part supplier tables listed and the attributes of each table. So let's now run a query against this particular DynamoDB table. I'm just going to add some quotes against this query and hit run. And in the background, again, Athena is calling our newly deployed Lambda connector and makes a call to our DynamoDB table. Okay, cool. We got a query result from our DynamoDB table. So that's pretty awesome, right? You've seen how you can easily deploy a connector and run a simple query against those different databases through a single interface. So let's now have a bit of fun and look at running some complex queries where we can perform some live joins across our data sources without the need to perform any ETL. So I'm just going to create a new query tab. And so let's paste in a complex query that I've used previously, which is going to provide us a list of all our active orders. Now, the query performs joins across a variety of data sources. We will be joining data from Redis, MySQL, HBase, and Dynamo. So let's now run that query, and we'll see what type of response we get back. Awesome, and there you have it. We can see how we have our active orders list now. So now let's take what we have configured and extend this into Amazon QuickSight to build out our dashboard, similar to the one that I showed earlier in the slides. So here we are in Amazon QuickSight console and an earlier version of the sales and order dashboard we saw in the slides. So what we're going to be doing now is taking the active customer order query we just ran in the Athena query editor and build a visualization for it. Before we can add that query as a new QuickSight dataset, the first thing we need to do is to configure the appropriate permissions to grant QuickSight the ability to call the DynamoDB data source connector. So if we head over to the security and permissions section found in the QuickSight configuration, and let's select add and remove and head into the Amazon Athena section, where we'll be able to see the S3 buckets we have granted Athena access to query already. And we'll also be able to see the corresponding Lambda functions for our existing HBase, MySQL, and Redis environments. So let's select the Dynamo connector and hit Update. Once we click Update, that will now give QuickSight the permissions to call the underlying Lambda functions where we want to query the DynamoDB via the Athena federated query. So let's now add the active order query as a new dataset. So if we select New Dataset, we'll scroll all the way down to a pre-existing Athena Federation data source. Select this, and then we can create a new data set. Now today we'll be providing a custom SQL query, but you can also see our different catalogs available here that we could also query. So let's use custom SQL, and we'll paste in our active orders query and give that query a name. We'll confirm the query and select Visualize. And we'll wait for the data source to be queried via Athena and import the query results into QuickSight's super fast parallel in-memory calculation engine, otherwise known as SPICE. So we've got the data imported now, and we should be able to create some visualizations for it. So we'll head back into the sales and order dashboard. So our final step before creating a visualization is to add the newly created active orders data. So let's now build a simple visualization for our active orders. So if we select Add a Visualization, now today I'm going to do a visualization using a simple table, and I'll select all the available fields. So now you can see the active order data, which is being derived from a federated query across our HBase, MySQL, Redis, and DynamoDB platforms. Let's now jump back over to the slides to learn more about what Athena Federated Query has to offer. Now you saw in the demo some of the connectors available for you to use. AWS provides pre-built connectors to enable you to quickly get up and running and query a federated data source like I showed in the demo. Beyond the connectors we used in the demo, you can find connectors from Amazon Document DB, Amazon Redshift, Amazon CloudWatch logs and metrics, and any JDBC compliant relational data source. In addition to the connectors for the purpose-built database services, AWS also provides a CMDB connector. Now this connector enables you to query your provisioned AWS resources using SQL. So for example, you can use this connector to query EC2 to describe your EC2 instances, security groups, and VPCs using a SQL query. AWS has open sourced all these pre-built connectors using the Apache 2.0 license, and you can find these on GitHub or the AWS Serverless Application Repository today. If you have a data source that you want to federate into Athena and it's not listed here, then you can use the Athena Query Federation SDK to build your own. You can use the example connectors provided on GitHub as a basis for your custom connector to learn how to implement the key features. Now, with Athena Federated Query introducing the ability to use AWS Lambda as an integration layer, it also has opened up the ability to apply code through user-defined functions to expand the SQL syntax. Athena UDF enables customers to write user-defined functions in Scala to perform custom processing such as redaction of sensitive data. Similar to the Federated Query data source connectors, you can write your UDF code, deploy it via Lambda, and invoke as many times as needed using standard SQL. Let's take a look at a UDF example. This is the code that we are using to perform the redaction of the sensitive data in the dashboard shown earlier in the slides. Shortly, we will see how easy it is to incorporate this into our own dashboard that we're building in the demo. But let's take a look at the code. The function is simple. We're taking a string input, we're redacting all characters apart from the last 4 and returning the redacted string. Once we have the code deployed in Lambda, we can then call this function within a SQL query. First, we declare our function and the parameters we will pass into it. Next, we declare the Lambda function itself. And finally, we can call our function within our query, passing a field as a parameter into the function to perform the redaction. Let's now jump back into the console and take a look at Athena UDF in more detail and see how we can apply it to perform data redaction within our dashboard. All right, so here we are in the Amazon QuickSight console, and so let's now integrate the custom UDF where we stepped through on the slide to redact the sensitive customer information. So to do this, we will need to edit the active orders dataset we previously created and modify the custom SQL we defined earlier. So the first step to integrate the UDF is to add a couple of lines before the query. Now this defines the Lambda function we will be calling and the redact UDF function name. And then we need to modify the query to pass the customer fields to the redact function. So if you hit apply and wait a second, we should see the query response now being updated and the customer details fields now being redacted. So if we select Save and Visualize and wait for Spice to be refreshed with the updated query, we can now see our dashboard updated to include the masked customer data as the UDF is being called. Now, the ability to use machine learning models in SQL queries makes complex tasks such as anomaly detection and forecasting as simple as invoking a function in a SQL query, removing the need for data users to learn complex data science frameworks. You can also use more than a dozen of the built-in machine learning algorithms provided by Amazon SageMaker, or you can train your own, or you can find and subscribe to a model package available in the AWS Marketplace. Let's now jump back over to the AWS console for one last time and take a look at Athena ML in more detail. So we're back in the Athena query editor, and we've got a really simple query to obtain a count of our customer orders from our orders database hosted on Aurora MySQL. So as we hit Run Query, Athena will invoke our MySQL Data Connector Lambda function to run the query and return the results, providing a count of orders made per order date. So to help us understand what the most likely order volume will be for a particular day, let's go ahead now and see how easy it is to integrate a machine learning model trained in Amazon SageMaker using Athena ML. So here's our existing query, modified to include Athena ML, allowing us to pass our data to our SageMaker model to perform anomaly detection on the volume of orders made on a particular day. So similar to the UDF example, we've defined a detect anomaly function, which will invoke a call to our SageMaker endpoint. So let's now jump over to the SageMaker console to grab that endpoint. Today we'll be using a pre-trained model using one of the optimized algorithms provided out of the box by Amazon SageMaker. So let's grab that name of the model that I've pre-trained earlier. We'll copy that and we'll paste that into the Athena query editor. Awesome. So the next thing we're going to do is we're going to use that same query I ran earlier and extend just a little bit to pass the order count into the detect anomaly function, which then in turn calls the SageMaker model that we just copied in to perform an anomaly score against it. So let's now run that query. As we run the query like we did previously for our MySQL data source connector, the Lambda function will be invoked, which will return the data from our orders database and then pass that order count onto our SageMaker model. Now, after a few seconds, we can now see the query results, which includes our anomaly score provided by our model hosted in Amazon SageMaker. Now, a low score value indicates that the data point is considered normal. High values indicate the presence of an anomaly in our orders. So let's now jump back into the QuickSight console and introduce this anomaly detection query into the dashboard we've been building. So firstly, we need to add a new dataset to QuickSight. So let's jump back into the dataset section and select new dataset. Similar to what we did before, we'll use the existing data source and we'll select create dataset. We'll again use a custom SQL option and paste our Athena ML query and we'll give it a name. And then we'll click confirm query. And then we can select visualize to import the dataset into Spice for quicker analytics. And now the dataset's been fully imported, we can now head back over to our sales and order dashboard and add our new dataset into this analysis. And now we can create a visualization for it. So let's select a stacked bar combo chart. Now this is going to help us compare the actual to our anomaly score being returned by our SageMaker model. Let's grab the order count and visualize it as a line graph. And we'll just change the aggregation to a sum. Next, let's grab the score and visualize it as a bar chart. And then finally, we'll track all this against the order date. But let's sort by date to give us a time series view of our orders. So let's zoom in to see which days are having a higher than expected orders being placed, which could then be incorporated into our downstream supply chain forecasting or manufacturing processes. The higher bar charts indicate the presence of an anomaly order. So that almost brings us to the end of today's session. Today we've explored how using Amazon Athena Federated Query, UDFs, and Athena ML can enable cloud-native data virtualization capabilities to help overcome some of your data integration challenges. We've also explored how easy it is to get up and running and query across heterogeneous data sources, removing the need for heavy data movement and apply lightweight data governance at the same time. We've also explored how using Athena ML can simplify accessibility of machine learning and enable machine learning models to be embedded into your data analysis via SQL. If you'd like to learn more, then please refer to the links provided. Here you can find material to understand more around the various components of cloud-native data virtualization on AWS. Links to the GitHub repo where you can find the source code of all the AWS provided connectors. But if you wanted to immediately get started and deploy your first connector, you can find all the AWS and partner provided connectors ready for you to deploy in your account via the AWS Server Application Repository in the console. And if you're looking to dive deep and sharpen your saw around the AWS purpose-built database services, AWS provides a range of online and instructor-led courses and specialty certifications. Check out the link provided here and look for the ramp-up guide to create your own learning journey. And thanks for joining me today. I hope you enjoy the remainder of the AWS Summit Online. But before you go, your feedback is really important to me. Please take the time to complete the survey. Thanks again.